ui. No, you see, I did it the other way around. Right, this should be ui. And here I take, I can take it on the other side. Okay. So now I take a sum lambda I e ui I greater than j, greater or equal to j, and I take e vi e vj wedge with this expression. Now this here we have one. Since all the indices are bigger than j, we know that e vj wedge e ui for I bigger than j is 0. And therefore this is equal by this condition, which unfortunately I use it for I and j replace. This is equal to e vj wedge or lambda j e vj wedge e uj. And for this to be 0, so this is 0, this implies that lambda j is 0. So the conclusion is that for the vector space version of the theorem, we can use the stronger combinatorial statement. And okay, once we proved it for the vector space, this also applied for the sets. So this proved the two family sets in the stronger. So this theorem has all sort of amusing history. We thought about it when we were graduate students, and at that time, Micha Perles knew this as a conjecture of Ehrenfrucht and Michalski. The statement, the weaker statement for I not equal to j, it was a conjecture of Ehrenfrucht and Michalski, and it was proved by Katona in response to their conjecture, and it was also proved by Bolobash before they made the conjecture. So there was a sort of a sandwich. The conjecture was sandwiched between a proof before the conjecture, a proof after the conjecture, and what? No counter example. And for a while, we used to call this version the diagonal Ehrenfrucht-Michalski theorem, which is the sort of the most misleading term, because it's not diagonal but upper triangular, and it's not Ehrenfrucht-Michalski theorem, it's Ehrenfrucht-Michalski conjecture, which was a theorem even before by Bolobash. So anyway, we used to call it this way, and the vector space version was proved by Lovas, and also, actually the skew version in slightly different version was conjectured by Bolobash. This stronger version, Lovas, and also several years later, I consider this vector space version, but Lovas didn't consider this stronger version. Anyway, but now we have all these proofs. One thing which is interesting is that this proof relies very heavily on the fact that we are walking over a field. So for example, we can ask a similar question. So perhaps the simplest way we can move to projective space, and then if we formulate it in projective space, this theorem says that if we cannot find 7 pairs of lines in a 3-dimensional projective space over a field, so that the 7 pairs of lines, L1, I don't know, L1, M1, L2, M2, and so on, L7, M7, so that L1 intersect, Li intersect Mi is empty, and Li intersect Mj is non-empty. So when we move to the projective space, the 0 is replaced by emptiness, and the dimension goes down by 1. So this is a statement about lines in 3-dimensional space. So maybe I'll say it again. So I think this is the simplest non-trivial case of this theorem. Again, translated to projective geometry, so if we have line L1 up to Ls, and the U1 up to Us, there are lines in projective 3 space over R, and if Li intersect Ui is empty, this time it's really empty, and Li intersect Uj is not empty if I is not equal to j. So I'm talking even about the stronger result, then this implies that S is less or equal to 6. Right? So this is the dimension of the... So the statement about lines in projective 3 space is the same as a statement about two-dimensional vector space in a 6-dimensional space. So this is the conclusion. And this is a nice theorem in a projective geometry. And the question is it true for all projective spaces? So we know that the 3-dimensional projective space of dimension 3 and above, they are always Desarguian. So they are always over a field of some sort, a skew field, a division ring. But this argument with the exterior algebra only worked over commutative rings. So we don't know if this is correct for other skew fields. For example, we don't know if it's true over the quaternion. So this is sort of an interesting, I don't have the slightest idea if it's true or not over the quaternion, even the weaker statement, or maybe, and it's sort of curious. I don't know, maybe over a division ring you can find as much as you want such a, I don't know, maybe it is true, but the proof certainly does not work. But I don't know enough about division ring to answer this question.
נתי, רצית שנעיר לך מתי יש שליטה?
מה השעה עכשיו? Okay, so we will make a break, and now, once we are equipped with this theorem, we will be able to prove this theorem. So we will take a break.